I'm Dr. T and welcome to my whiteboard. Today I'd like to talk about formula weights. The idea actually gets a couple of different names depending on context. You'll quite often see it as molecular weight, molar mass, or formula weight, depending on your context, but the ideas are more or less interchangeable. Molecular weight implies you have a molecule. Formula weight generally implies it's the empirical formula, but not necessarily. And molar mass is probably the best to use, except for the fact that there are so many things with M in chemistry that there's actually a pretty good deal of confusion. So just to alleviate confusion, even though it's maybe not the most optimally from a technical subcontext perspective, I typically use formula weight myself. Once again, now this is the same idea. Your textbook will probably use molecular weight. Okay, what am I talking about? Well, let me jump into this. So to give some context, we need to know a concept called Avogadro's number. So Avogadro was a researcher quite a few years ago, did work with gas laws and understanding the nature of gases. We're going to see him again later on. From his work, he got the idea that, hey, atoms probably could be counted. Actually, this is before we knew that they were atoms, but we kind of had a hunch that there were atoms. And from this, we wanted a conversion factor from grams to these molecular weights that we were starting to work out, what we now know as Daltons. So this conversion factor is basically what a gram divided by this number would equal a Dalton, and that's going to be Avogadro's number, a little over 6.022 times 10 to the 23rd. There's a few more digits there. The definition has changed just a little bit. It's actually kind of a little bit wonky at the moment, but the basic idea here is this is the conversion factor from the world of grams to the world of Daltons, so that, hey, if I've got an atom that has, say, a mass of 12 Daltons, probably carbon 12, then a mole of it, or Avogadro's number of this atom, will have a mass of 12 grams. Now, that leads me over to what I just said. Avogadro's number of a thing, forgot the G, is going to be known as a mole. Not the furry critter, although it is spelled the same. Now, you will see it quite often, M-O-L-E, that's the English spelling of mole, although you will also see it very, very commonly in the German spelling, M-O-L, and this actually tends to be more popular for the fairly straightforward reason that it's a 25% savings on characters. You know, get rid of the E. So what are we going to do with this? Well, with the moles, when we jump into stoichiometry, this is how we're going to start tracking atoms. Atoms are ridiculously, ludicrously small. A glass of water, actually not even a glass, a shot glass of water, so not much water, is going to have about a mole of atoms, and that's about as many atoms as there are grains of sand on all of the Earth. That's a lot of atoms, because they're really small. So we're not going to be counting atoms individually. Instead, we're going to be working with them in moles. And in order to do that, you can't count them 1, 2, 3. Yeah, you'll never get done. So instead, we have to count by weight. We need to know this conversion. We need to know the mass of our atoms. And hey, we have a periodic table for that. But quite often, we're not working in atoms. We're working in molecules or empirical formula units. How do we work in those when they're not on the periodic table? We only have elements on the periodic table, only atoms. Well, to do this, we need the formula weight. The idea here is that the mass of your compound divided by its formula weight will yield you the number of moles of whatever the compound is. Likewise, moles times formula weight will give you the mass. Well, how do you find this formula weight? What you're going to do is basically just add up all of the atoms in your compound. So if I take, say, something like cobalt chloride pentahydrate, what I'm going to do is simply add up the masses of every single atom in there. So 58.93 for the cobalt, 35.45 for the chlorine. Now, here's the catch. We've got 2 chlorines, so I times it by 2. Likewise, the water. Each water has 2 hydrogens, an oxygen, and in this particular case, I have 5 waters. So, I have to times the whole thing by 5. Sum that whole mess up together, and I get my mass. Likewise, if I'm doing, say, calcium phosphate, Same basic story. I've got the mass of the calcium. Because I have 3 calciums, I'm going to multiply it by 3. For the phosphates, I'm going to add together the phosphorus and the 4 oxygens, and then multiply that all together by 2, giving me my formula weight. Now with this, I can do other things, specifically convert to and from moles. With that said, have a wonderful day.